Lecture video for November 30th through December 1st. Starting a new unit today on polynomials. One of the things we have to do with polynomials is classify them, so I thought we could have a little bit of fun here with the dichotomous key and classify some aliens first. Specifically, I'll embed a question for you to go through this dichotomous key and come up with the scientific name for this alien right here, the third one in. So go ahead, follow this, come up with the name for this alien here. Okay, so our goal is to be able to classify polynomials as well as identify their end behavior, number of terms, and convert to factored form. We're going to be doing a lot with polynomials today, so definitely get those notes out. Why are we looking at all these different features? Well, the classifying is going to help us have a way to talk about polynomials. And all of the different features are going to help us visualize the polynomials before we start a problem. You know, whatever we're being asked to do, it's always useful to kind of have a picture of the polynomial in your head. All right, so what is a polynomial? Really, we've been dealing with polynomials all semester long. We just haven't been calling them polynomials. But any mathematical expression composed of multiple terms is a polynomial. Poly means many, nomials are referring to the terms, the numbers, many numbers. So here I've got a bunch of examples of different polynomials for you. Let's go through them one at a time, write them down, and then we're going to write a name for this polynomial, classifying it by either its degree or its number of terms. All right, degree, that's a vocab word for you. That means the largest exponent in an expression. All right, if we don't see any variable, then the largest exponent would be a 0, meaning that this one here is a constant. Without a variable, this expression can never change value. It's just a 5 forever. So we call it a constant. Now, how many terms are there? There's just the one term, so it gets the name monomial. All right, next one. Well, there is a variable there. The largest exponent on that variable would be a 1. When the largest exponent is a 1, it is a linear expression. And you can see this 8x plus 2, that kind of looks like the right-hand side of y equals mx plus b, which we know is a linear equation. This has 2 terms, so it's going to be called a binomial. All right, what's the biggest exponent in this one here? Go ahead, copy down our third polynomial, 3x squared plus 5x plus 1. This is in standard form because it's in descending order of exponents. It goes 2, 1, 0. The biggest one is 2. The word for this one is a quadratic. Just finished up a whole unit on quadratics. And count up the terms 1, 2, 3. The terms are anything that's glued together by multiplication, separated from one another with addition or subtraction. This is a quadratic trinomial. All right, biggest exponent on this next one, 4x cubed plus x is a 3. The word for when the biggest exponent is a 3 is a cubic. In this one, we're back to a binomial. Just because our biggest exponent is a 3 doesn't mean we have to have a quadratic term and a constant term. Because we skipped those, this is just a binomial expression. Next one, the biggest exponent is a 4. The word for that is quartic. This is our root word for 4, quar. This is a quartic expression, and again, it's back to a trinomial. All right, copy down this next one. It's much longer expression, but all we have to do is look for the biggest exponent to figure out how to classify it. The biggest exponent is a 5. This is going to be a quintic. And after we get to 4 terms, this terminology gets a little bit less exciting. You just say polynomial of 4 terms. So this is a quintic polynomial of 4 terms, this whole expression here. All right, last one. Biggest exponent is a 6. So this is where degree stuff's going to be exciting. After the 5th degree, you just start saying 6th degree, 7th degree. So here's a 6th degree polynomial of 6 terms. And that's all we would say for this one. We would be able to continue that pattern up to infinite number of terms. You just keep saying polynomial of blank terms. There's only special words for monomials, binomials, trinomials. Same thing with degree. After the 6th degree, you just go 6th, 7th, 8th degree, up to whatever number you want. There's only special terms for constant, linear, quadratic, cubic, quartic, and quintic. All right, so when you're talking about a polynomial, you can call it just by the name for its degree or just by the name for its number of terms. But if you're going to call it with both, you always go in this order. Name for the degree, name for the number of terms. So let me pop up another polynomial on the screen here. We have y equals 5x cubed plus 3. So this expression over here, this is a cubic binomial. All right, so now we have a way to talk about this expression. We can say, next we want to input our cubic binomial into this expression, something like that. And we'll know what we're talking about. We'll look for the one that's got an exponent of 3 and contains 2 terms. All right, can we go the other direction? If somebody asks us for a quartic polynomial of 4 terms, what would be a possibility? Well, to make it quartic, we just need to make sure our biggest exponent is a 4. All right, so let's make this a term. So make it maybe 3x to the 4th. Now I can fit in 4 more terms. So as I add in more terms, I can give them whatever exponent I want, as long as I don't repeat and I don't go over 4. So maybe I'll make this next one an 8x cubed. Now I've got 2 terms. The next one plus 9x, and then minus 5. And I've got 1, 2, 3, 4 terms. Biggest exponent is a 4. So this is a quartic polynomial of 4 terms. All right. So when we go to graph polynomials, if they have a high degree, they might squiggle around a bunch. So let me just kind of pull up some blank paper here. This is a typical polynomial. The high degree one might do some squiggles like this, but eventually they always pick a direction and stick with it. So they might go up and down for a little bit, but towards the tails, they stop going up and down, and they start either going down forever or up forever. And that's what we're talking about with end behavior. End behavior is always measured from the middle out. All right, so middle out. So this would be considered down end behavior, because if I go infinitely to the left, I'm going down, or if I go infinitely to the right, eventually I will start going down. I might go up for a little bit, eventually I'll start going down, I'll never stop going down. All right, so here's kind of a little table to help you figure out what the end behaviors are. For any polynomial, you only have to look at 2 things. You have to look whether the degree is even or odd, so whether the biggest exponent is even or odd, and then whether or not the leading coefficient is positive or negative. So go ahead, pause this, copy down the top part of that table there. You can show it with the pictures, and then let's fill in the words for these different end behaviors. This one here, an odd positive, I call this down, up end behavior. And you can just call it that too, just literally say down, up. Odd negative would be up, down end behavior. Even positive goes up, up, and even negative goes down, down. All right, now a quick note on number of turning points. So what I said is polynomials can squiggle around a whole bunch, going up and down, up and down, up and down. The maximum number of times they can turn is one less than their degree. So this one here, my example turned 5 times. So this has 5 turns, where you go from having a positive slope to a negative slope, or from a negative slope to a positive slope. All right, that means that this is at least a 6th degree polynomial, because the number of turning points is always 1 less than your degree, so n minus 1. And just think about a parabola. Parabola is a 2nd degree polynomial, and it is allowed 1 turning point. All right, quick shortcut to remembering end behavior. So the end behavior will always match the leading coefficient going to the right. So positive means up, negative means down. And then once you know that, you've locked one side in, and then you use the degree to see if the end behavior should match. If it's an even, then they do match, so it's either up, up, or down, down. If it's odd, they don't match, which, since there's only 2 conditions here, guarantees that you would know what the other side's doing. It would be either up, down, or down, up. All right. So using that information, we can kind of get a sketch of a polynomial going. Go ahead and copy down this polynomial, y equals negative x to the 4th plus x squared. We're going to use what we know now about end behavior and number of turns to do an okay sketch of this. So this polynomial here, we could say it is negative because it has a negative in front of its biggest term, meaning its leading coefficient is a negative 1. All right, and then the degree is a 4, but all I care about that 4 is just that it's even. All right, number of turns is that 4 again, but you have to subtract away 1, meaning we can have a maximum of 3. We don't have to turn 3 times, but we can't turn 4, 5, or 6 times. That's our max. All right, so using just that information here, plus there's one other free piece of information, and that's the y-intercept. If there's any constant at the end, that's always the y-intercept. Using that information, we can get a somewhat decent sketch of this. So it's negative and even. Negative means it'll finish down. Even means the end behaviors match. So this is going to be a down, down end behavior with a y-intercept of 0 and a maximum of 3 turns. So maybe it looks like this. 1 turn here. 1 turn here. 1 turn here, and we finish going down. So this is down, down with 1, 2, 3 turns and the correct y-intercept. So we have got kind of a general shape of this graph. We don't know exactly where these humps are, or even if it does turn 3 times. This is just kind of a possibility. It definitely couldn't turn more than these 3 times. All right, another one for us to try. Go ahead and write it down. This one we'll say is an odd negative, y-intercept of negative 6, and it can turn twice. Biggest exponent is a 3, but you always subtract 1, so we can have 2 turns. Okay, so odd, negative. Negative means it will finish down. Odd means that they won't match. So this has got to have up, down end behavior. Y-intercept of -6. And then we can put those 2 turns kind of wherever we want, just to see what this graph could look like. So here is our sketch. It's not perfect. We don't know, the x-intercepts, for example, or if this turn happens to the left or the right of the y-intercept. But we can get the general shape. We got the correct end behavior, the correct y-intercept, and the correct number of turns. All right, now looking at a graph, can you figure out what kind of polynomial caused it using these rules for number of turns and end behaviors? So sketch a quick one of this first graph here. We can see it turns 1, 2, 3, 4 times, so 4 turns. Means that at a minimum, this must be a quintic, but it could be something even higher. But we'll say quintic. Also like quintic because we can see it's got down, up end behavior, which can only happen with an odd degree. So this is quintic. And for it to finish up, it's got to be positive. So we're going to say it's going to be odd positive. All right, next one, I see 1, 2 terms, meaning that the lowest degree it could be would be a 3rd degree. So this is probably cubic. 3rd degree is cubic. It has down, up end behavior as well. So it's also positive leading coefficient. We'll say odd positive, even though cubic implies the odd part. All right. So I'm going to take a quick break here, and then we're going to talk about factored form. All right, so you already know about factored form because when we broke a quadratic apart into factors, we were converting a polynomial into factored form. Well, that can be done with polynomials of any size. Here we've got a cubic, for example. We're going to break this one apart into linear factors. And there's a lot of techniques here. We'll start with just some basic ones and progress throughout the unit into more advanced factoring techniques. But this one here can be factored using techniques you already know, starting with factoring out the greatest common factor. Every single term here has an x, so I can go ahead and take an x and write it out in front. And I'll put parentheses around it so it's its own linear factor. All right, what gets left behind? Well, an x squared minus 2x minus 15. All right, so this is a quadratic factor, but this is kind of like factored form, but it's not considered to be true factored form until everything is linear factors. But this piece here can be factored just using simple factoring. So I can write out my 2 linear factors and then ask the question, what 2 numbers multiply to be -15, but add to be -2? Those numbers are a -5 and a +3. Those 2 multiply to be -15 and add to be a -2. And now this is all the way factored. This right here is considered factored form. Maybe label it as such and say that these pieces are linear factors. All right, Now you can go the other direction, starting with factored form and going back to standard form. Standard form is when we get rid of all the parentheses and we write it in order of descending exponent. So if I need to convert back to standard form, I'm just doing distribution. A binomial to a binomial, we need to FOIL that. So first outside, inside, last. And we'll get x squared minus 4x plus 3x minus 12. I still keep it in a set of parentheses because this whole piece over here still needs to be distributed to this x plus 5. Here, let's combine our like terms. We'll make this x squared minus x minus 12 times x plus 5. Now I can't FOIL because this isn't a binomial and a binomial. It's actually a trinomial and a binomial. So when I go to distribute, I just make sure I get every combination possible. And I often will say it like this: first to first, first to second, second to first, second to second, third to first, third to second, so that I make sure I'm following a pattern. So like this, and then like this, for a total of 6 combinations. All right, and let's see what we get. X squared times x becomes an x cubed. X squared times positive 5 is a plus 5x squared. Negative x times x is a negative x squared. Negative x times 5 is a negative 5x. We get a negative 12x and a minus 60. And we combine like terms. Y equals x cubed plus 4x squared minus 7x. Why, that's a negative. Minus 17x minus 60. And that is distributed and written in standard form. No more parentheses, and the exponents go 3, 2, 1, 0. So descending order of exponents for our terms. All right, here we've got a polynomial in factored form. We're going to keep it in factored form because if we want to find the zeros, factored form is actually really helpful. What we can do is we can still apply the zero product property even though we've got 3 factors. Just go ahead and set each of these individually equal to 0. And it works the same way the zero product property worked with quadratics. The idea is it doesn't matter what you're multiplying. If one of those things becomes 0, the whole thing will be 0. All right, so I set each of these individually equal to 0. And what I'm solving for are the x-intercepts. All right, so even though I don't know a ton about what this graph will look like, from the factored form, I was able to get 3 of its x-intercepts. Those were -2, 1, and 3. We see we have 3 factors, so this can be a cubic, meaning it can turn twice. So we're not sure entirely how it's going to hit these 3 points, but we know it's going to turn twice, and it looks like it's going to have a positive leading coefficient because none of these x's are negative, meaning that it will finish up, and because it is cubic, the end behaviors don't match, so we get down, up. All right. Now, if you are just told the zeros, you can go ahead and write a function by just reversing that zero product property. For there to be a 0 at -2, then there's probably a factor of x plus 2. So that when I plug in a -2, this becomes a 0, and we've got an x-intercept. If I see a positive 2 here, I'm going to put an x minus 2 to make sure that this number triggers a 0. And then when there's 0 at 3, we'll just put in a linear factor at x minus 3. And it's just as simple as that. Just as simple as flipping the sign on the zeros when you put it into the linear factor. We don't need to get fancy with any coefficient on x, just like this is fine. All right, can you have two zeros in the same place? So same thing, but I've got an extra 0 at -2. Is that okay? So algebraically, that's totally fine. We're just going to add in that factor twice. What does that look like graphically, though? So what that looks like is right at -2, our graph's going to do something a little bit funny. Let's see, this is going to have up end behavior. So right at -2, the graph is going to just bump the x-axis, but then turn and go back. All right, and we also need 0 at 2 and 3, and we'll finish with up end behavior. So right there, this where it just touches is what we call a double 0. And then the other two zeros are just single zeros where it told us to put them. All right, another one to practice factoring with. Copy this one down. Just algebraically, can we find the zeros of this one? So I do see a greatest common factor. I can pull out an x squared, leaving behind an x squared minus 2x minus 8. And then it looks like this can be factored further with simple factoring. Are there two numbers that multiply to be -8 but add to be -2? I think those numbers are -4 and +2. All right, and here are our zeros. We're going to apply the zero product property. X squared, being by itself, is going to give us a 0 at x equals 0 with a multiplicity of 2. The x minus 4 being a linear factor means +4 will be a 0, and x plus 2 being a linear factor means -2 will be a 0. The only one with the multiplicity was this one at 0 because it had this squared. If you have a repeated factor, you can get a multiplicity at different numbers as well. All right, let's talk real quick about relative maximum and minimums. If we look at this function here, it really has no maximum or minimum because this side goes down to -infinity and this side goes up to +infinity. But it might still be worthwhile to figure out what the max was of just this hump here, or just the minimum of this hump here, just so we know where these features are in the graph. So those humps are called relative maximums and minimums. So for a given range, that bump right there is the maximum. All right, so we're going to do this with a calculator. We're going to try it with this function here. Got to get out my calculator. You should do so too. We're going to sketch this and then figure out where its relative minimums and maximums are. All right, so press y equals and enter in this expression here. X cubed. Let's clear this out. X cubed plus 3x squared minus 24x. All right, I'll do a zoom 6 to just get a kind of a standard viewing window here. I can see I kind of need to go up in the y direction, so I'll change my y minimum and maximum to maybe be -30 and +30. Now let's take a look at this graph. Still can't see that maximum there, so I'll increase the y maximum up to I don't know, 100. I couldn't see the y minimum super well. Maybe I'll drop this down to -40. Take a look at this graph. Okay, so now that I can see the relative maximum and minimums, I can use this trick here. Second, calculate, a little calc up there, and you see options 3 and 4, minimum and maximum. That's what we want. So I'll do the maximum first. So I'll press 4. And it says, it starts asking questions at the bottom. Left boundary. So I need to pick a number that's obviously to the left of this maximum here. So maybe I'll pick like -7. All right, so now I've set up a boundary on this side of our relative maximum. Now I got to set up a boundary on the right side. So maybe I'll pick 0 for this one. You can see it's put another line over here. And then it says take a guess. Now this isn't super important unless you've got multiple maximums in one interval, in which case you should just constrain your constraints a little bit more. You can take a guess, you cannot, you can just press enter, and here's what it comes up with. -4 point, and then a bunch of zeros and a 2. This is probably just the calculator's rounding error, and it's really at -4, and then the y value is 80. So we've got a relative maximum at -4 comma, did I say 80? Did I say 70? What did I say? -4 comma 80. -4 comma 80. And let's try that again to find the minimum, this little minimum over here. So I'll clear. This time I'm doing second. Calculate number 3 for a minimum. I need a left boundary. Maybe I'll pick 1. I need a right boundary. Maybe I'll pick 4. You can see I've got those 2 lines on either side of this minimum. It says take a guess. I'll just press enter, and it brings me right on top of that minimum to 2 comma -28. And that is our relative minimum. All right, maybe some parentheses, you know, these are ordered pairs. And that'll be that for this lecture video. I'll embed a few more questions here, and have a great rest of your day.